Tere kõigile! Alustame tänase webinariga. Mina olen Terje Korberg. Tänan kõiki, kes on liitunud meie tänase webinariga. Tänast webinari korraldab Arukad Süsteemid, kes on Autodeski Gold-partner ja autoriseeritud koolituskeskus. Arukad Süsteemide missiooniks on tarnida ettevõtetele kasulikke tarkvaralahendusi. Ehk siis lisaks tarkvara müügile pakume ka koolitusi ja konsultatsioone. Meie avatud koolituste valikust leiab lisaks Fusionile ka AutoCAD-i, Reviti ja teiste tarkvarade koolitusi. Täna toimub esimest korda meie webinar inglise keeles ja seda viib läbi meie uus konsultant Drew ettevõttest Northwind Engineering. Eelmisi webinare on viinud läbi meie teine konsultant Tõnu Leimet Maaülikoolist ning kõikide nende webinaride salvestused on nähtavad meie kodulehel. Lisan webinaride ja koolituste lingiga chatti. Kui teil tekib webinari ajal küsimusi, siis palun kirjutage need chatti või siis tõstke käsi ja me avame teie mikrofoni. Palun kirjutage ja küsige webinari ajal inglise keeles. Küsimuste ja vastuste voor on ka lõpus. See on minu poolt kõik ja annan nüüd sõna edasi Drew'le. Word to you, Drew. Thank you.
Great. Thank you for the introduction, Terje. I will just share my screen. And okay, so as Terje mentioned, I'm going to be going through a workflow example for a static simulation in Fusion 360. And also I'll mention kind of some of the best practices that I've established over the years. And as she also mentioned, you can write questions into the chat, or you can raise your hand and just ask over the microphone at any time. So just tell you about myself. I'm the CEO and principal consultant at Northwind Engineering. We're located in Tartu, Estonia, and our core business is modeling wind turbines, full system aero servo hydroelastic modeling. So basically we run simulations which produce the loads, and those loads would then feed into a structural analysis, for example, using Fusion 360. So we use Fusion to design and analyze the steel parts that are used in the turbine. We also do lots of coding to post-process the simulation results, and we have all kinds of tools in MATLAB and Python mainly. We have clients all over the place: Canada, US, UK, Denmark, France, Germany, and Estonia. And feel free to get in touch if any of this sounds interesting to you. So now I will switch over to, I'll go through the kind of overview of the presentation. So we'll just go through right from the beginning through a full workflow. So everything from importing the part, applying constraints and loads, making sure we have proper geometry, setting the contacts and the mesh, and then looking at the results. I'll also show how to analyze multiple load cases and taking advantage of symmetry to simplify your analysis. And I'm going to show two different examples just to give you a flavor of the kind of situations you might run into. So I'm going to now switch over to Fusion. Just one moment. And while we wait here, actually, I would like to ask everyone here a question. How many of you are already using Fusion and running static simulations? If you can just raise your hand. See if we have any. No? Okay, here we go. 2 participants. Good. So then at the end, you can tell me everything that that you know better than me, and I can learn from you as well. Okay, I'm going to share Fusion now. So here we are. Now, as I mentioned, we're going to go through the full workflow. So usually you start a new file, and then you have to save it before you can import the geometry. I can't see my bar here, just 1 minute. There we go. So we'll just save the file. And we're going to look at what's called a root extension for a wind turbine. Here it is. Oh, okay. Now this is a part that basically extends the length of a wind turbine blade. So you would attach the blade at the end here, and the inner part would attach here to the hub. So the hub is where the 3 blades come together. And this is an assembly, so it consists of multiple parts. And this is actually from the production drawings of the parts. So and this can come up this is quite common. So you have to really look at the interfaces between the parts, because in your FEA study, you want to be sure that you're actually simulating the part that you expect to have in operation. So for example, you can see these stiffeners have some chamfers on the corners because they would be welded to the tube. And we need to simplify this geometry or modify the geometry within the FEA study to get a realistic contact area between the stiffener and the tube. Because at the moment, we just have this very small contact area, whereas under these chamfers, the weld would fill it in. So if you just ran the study like this, you'd have a much smaller contact area between the parts and probably unrealistically high stresses. So just want to point that out. We have some other chamfers as well, where the tube meets the ring on both ends. So now that we have the part in here and I've kind of explained how it works, we'll go ahead and create our simulation. Now we have a couple options. We only use static stress simulations. You have the option of using a nonlinear simulation. That's when you're basically operating in the nonlinear part of the stress strain curve. But our parts are always designed to stay within the linear portion for obvious reasons. So that would be this portion of the stress strain curve here. So we're going to run a linear static stress simulation. So here we are. Just open up this browser. So I had mentioned the geometry and the fact that we have to make some modifications. So we'll do that first. And to do that, we go into the simplify environment. And as I mentioned, we want to eliminate these chamfers to get the correct application area between the parts. So it's quite simple. You just click on the surface and delete. And of course, it'll make some assumptions about what the shape should end up being. So you want to be sure that it produces the result that you want, but in this case it does, it's fine. And we'll just go around to the other chamfer. And you can see when I delete one chamfer from one part, it applies it to all of that same part within the assembly. So we only have to do it for one part. So that one is good. I had mentioned we have some chamfers in the ring here. And to give you a better kind of visual, we can go to the section analysis. And so now we're looking at a cross section. And you can see here that where the tube enters this flange or this ring, we have some chamfers. So, sorry. We'll just create that section once more. And we'll delete this one. Geometry looks good. Now this is a situation when I delete this one, you'll see that actually it removed the material rather than filling the material. So this is a situation that we're gonna have to correct because in the end, the material will be full in this corner. And to do this, we can use what's called a pull operation on the tube. I'll just get a better view here. So what we're going to do is pull this surface of the tube so it's in line with the surface of the flange. So how far do we have to pull it? We'll just measure 5 millimeters. And we'll do modify, press pull, and we'll just pull this out 5 millimeters. So now we have the geometry that we expect after the production of the part. And we have just a couple more chamfers over here. I'll just get a better view. Here we are. So that's good. And that's good. So now we have the proper contact areas between the parts. And one last thing that we should always check is interference between the parts, especially if you've done some simplification operations. So I'm just going to turn off the section view, and we can use this interference option. So I just go and select all of the parts. And we will check for interferences. And lo and behold, we have some interference, and that is due to the fact that we deleted those chamfers, and due to the curvature of the tube, you actually have some interference between the stiffener and the tube. So what this interference does is it identifies those where you have this kind of overlap, and then you basically just want to delete the overlapping sections, and now you won't have any interference when it comes to meshing. So our geometry is good now. So we have something in the chat. There are still chamfers on the stiffener plates. Ah, good point. You're paying attention. So I forgot about these chamfers. There we go. One more. Thank you for that. And now it should be fine, but please let me know if I forgot something. Simplify, finished. So we have our simplification. Now we can go and set our constraints and loads. In this case, as I mentioned, this inner ring will be bolted to the hub. So we just select the area that will be in contact with the hub. And we're assuming that it's bolted such that we essentially get a equivalent to a bonded connection. And that should be fine if the bolts are properly applied. And then we will add some loads. As I mentioned, the blade is bolted to this end, so here. And I'm going to apply 2 loads. One of them is the centrifugal load due to the rotation. So I'll just change the direction. So we're using this kind of angle option to define the direction of the load. And in this case, the load is 7 kilonewtons. I'll put 7 times 10 to the 3 newtons. And I'm going to put a moment as well. And we will also change the direction so we get the proper angle. And we have 16.2 kilonewton meters. Note the units here. are in Newton meters, Newton millimeters. So we'll just change it to Newton meters. And 16.2 kilonewton meters. Good. And now I mentioned we can analyze multiple load cases. So the way I usually do it is I set up the first one, so we get all the directions oriented correctly, and then just right click, clone load case. And now we have a second one. And we can go and put our forces in for this load case. In this case, we have 10 kilonewtons and a moment of 20 kilonewton meters. You also have the option of turning gravity on or off, depending how you've defined your loads. In this case, I'll just leave it off, but if you turn it on, then you get this gravitational vector here. So we got our geometry set up, we got our loads, our constraints. The next thing is the contacts, which can be done automatically. So automatic contacts. You have to establish this detection tolerance. So whatever you put here, in this case 0.1 millimeters, it will create a contact between any parts that are within this tolerance. In my case, that's fine. You might have some situations where some parts are this close, but you don't want a contact. So I'll show you how to check them after. So generate the contacts. And to check that all the parts are fixed properly, we can do this degree of freedom view. So everything is fully fixed. So that's what we want. And then we can go and just have a look at the contacts if you want to. Manage contacts. I like to list by the body. And then, for example, we have this first flange, and you can go through each contact. So the flange contact with the tube. So you can see this purple strip is where they're in contact. And then all the different stiffeners all the way around. So that's another way to just be sure that you have all the contacts you want and that you don't have any contacts that you don't want, which can happen sometimes, as I mentioned. So contact, good. Loads, good. Constraints, good. Geometry, good. What's left? The mesh. And in this case, we have parts that are 10 millimeters thick, like this flange, 10 millimeters. The stiffeners are also 10 millimeters. And the tube is 5 millimeters, as you'll see. Now, the rule of thumb I use, which is based on some studies, is if we're using parabolic elements, then we can set the mesh resolution equal to the thickness of the part. And the default in Fusion 360 for the type of element is parabolic. So what that means is you get a node in the middle of the curved element. Now, if you switch to linear, then you don't have a node in the middle of the element. So you should technically put at least 2 elements through the thickness of a part. But we'll stick with parabolic. And because we have parts with 2 different thicknesses, we're going to make use of the local mesh control option. So I will start with the tube body selection. So for this body, as I mentioned, we'll set the resolution to 5 millimeters. And we'll do one more for the 10 millimeter thick parts. And I'll just select them in this way. So I don't have to go around and individually select. It will automatically deselect whatever already has a defined mesh. So that looks good. And then we set the mesh to 10 millimeters. So at this point, we have ticked all the boxes. You can even see from the pre-check that it has all the information required. So at this point, you have the option, you can generate the mesh prior to running the simulation, which I'll do sometimes just to be sure. Or you can just solve the simulation and it will do the mesh generation as well. So I've kind of pre-generated the results here, so we don't have to sit around and wait. So I'll just switch over to that one. And first I'll show you the mesh. So as you can see, we have a 10 millimeter mesh on the 10 millimeter thick parts, and you can see this finer mesh on the tube. And then we can go ahead and look at the results. Just a moment. Results. So you can see the stress distribution in the part. I pretty much always look at the von Mises stress. You can also look at safety factor, but then you have to be sure about your material properties. They define the ultimate or the yield stress correctly for your material. For me, it's just more straightforward to stick with stress. And of course, you can inspect it in all kinds of different ways. We can do a slice plane. So we can have a look at some of the kind of internal stresses if we wanted. We can do a surface probe, which is also handy when you want to look at the kind of higher stressed regions. So for example, here we can see how the stress increases in some of these locations. And pretty much that's it. That's the workflow that I follow. I didn't go through all the options. Oh, one more thing, if you want to, you can have a look at the deflection. It's kind of exaggerated here. You can look at the actual deflection, which isn't so noticeable by the naked eye, but there you see it, as expected with the load and the moment applied. And I mentioned the multiple load cases. You can switch between them here. And if you want to reset the scale, you just double click. And for example, if you want to reduce the maximum, you can do something like that. So that's the kind of first example. And if anybody has any questions on this, feel free right now. I don't see any. You can also just chime in anytime. And if not, then I'm just going to move on to one more for a different part. So where is it? Yes. This is the hub assembly. So this is where the blades are bolted and the root extension is bolted. And this is a case where rather than modifying the geometry within the simulation environment, within that simplify environment. Oh, we have a question. Do you have a rule of thumb for the mesh size? Well, as I mentioned, usually I go with the thickness of the part if it's kind of a hollow cross section or a plate. Sometimes that can be an issue if it's like a very long tube, for example, and you have too many elements. But in that case, the smarter thing is to kind of chop your tube up, for example, into smaller sections. But overall, as I said, with parabolic elements, I go with the plate thickness. But the best practice really is to do a bit of a convergence study, so you can run your simulation with kind of a few different scales of mesh and check that that you're converging, that the stresses are converging. So I hope that helped. Now, second example, as I said, this is a case where rather than modifying the geometry within the simulation environment, I would just redraw the part, just a kind of FEA specific model, because here, for example, we have these open corners that will be welded. We have a bit of a milling operation that will be done here to smooth this section. So it introduces some complexities in the geometry. Again, some chamfers, stiffeners. So in this case, I just drew I just made a new drawing, and that's what this is. So you can see we have a nice continuous connections between the parts now, and that will enable us to do a proper FEA study without messing around in the simulation environment. And as for how I do that, you guys probably already know how to create parts, but just some simple kind of lofting. I drew the front and back, lofted between, then I lofted out the intersection and started creating the plates on either end. Then we had where the blades are bolted, and finally the holes and some circular patterns just to finish it off. So that's just kind of the approach that I take sometimes. Now, we can jump right into the file. This one. So I've already kind of set up the simulation since we've already gone through it once with the root extension. And the point of this one not only was to show, the idea of just drawing a new model for the FEA study. I'm going to show how I go about using symmetry to kind of simplify the analysis, and it also speeds it up. You need less computing power. And the other thing I'm going to show is splitting a face. So in this case, you can see where the blade will be attached, or the root extension will be attached. The flange will only extend just beyond the outer part of the bolt's holes. So we need to define an area where we can apply the loads rather than applying them to the entire surface of the plate. So I'll show you how to do that. But the first thing is symmetry. So if you want to use symmetry, you have to think about three things. First of all, geometrically, your part needs to be symmetric. In this case, it's true, and we have symmetry in kind of three planes, 120 degrees to each other. On top of that, the loading has to be symmetric. So the three blades will undergo essentially the same loading, or we can assume that the loading is close enough. So we'll be getting the same load applied to each plate. And then you have to think about whether the stress distribution in the part will also be symmetric. And in this case, because the geometry is symmetric and the loads applied are symmetric, we can also assume that the resulting stress will be symmetric. So the idea is that you don't want to miss the kind of the limiting or the extreme stress in the part by cutting out part of it, and then turns out that the max stress is somewhere else. So it takes some thought, but if it's if you can tick those boxes, then you can go ahead and use symmetry. And to do that, we'll again go to the simplify environment. Now what I'll do is just basically just draw a sketch on the front surface here, and just kind of do an extruded cut to cut out the 2/3 of the hub. So I'll draw a circle like this. I'm going to project the plate just onto our sketch plane, so I get these points available. In this case, I'm going to cut out, I'm going to keep the lower 1/3. So I'm just going to draw these lines like this. Finish my sketch. And now I can just do a simple extruded cut, and you'll see, oops. And there we are. So now we have our geometry just as 1/3 of the hub. And as I mentioned, we also want to define a circular area where the flange is bolted on. So I'm going to do another sketch. And in this case, my flange was 450 millimeters. So this sketch defines that circle. And then we're going to use what's called the split face option. Choose this face. Our splitting tool is that circle that we just drew. And there we have it. So now you can see that we can select a circular area where the flange will be bolted. So now we have our geometry, we have our face. And the only thing when it comes to symmetry is a particular extra operation with the constraints. So we'll start with our fixed constraints. You're always going to have some fixed constraint. In this case, it's where the gearbox shaft, where the hub is mounted on the gearbox shaft. And when we do this symmetric cutout, we need to use what are called frictionless constraints. And those apply anywhere that we've sliced through the material. So here, oops, here, and there. And what a frictionless constraint does is it prevents the surface from moving or deforming in the normal direction relative to the surface, because obviously there would actually be material there. It would be continuous all the way around. So this kind of takes care of that. And beyond that, you would just follow the same steps we already followed with the other one. So I don't think I'll repeat that. I think our timing is pretty good now. And at this point, yeah, I'll just say thank you, and happy to take any questions anybody might have. No? Maybe nothing in the chat. Okay. I also wanted to mention that I do offer private consultations if you want. Just get in touch, or just design services overall. And if you have any ideas or any requests for any other webinars regarding Fusion 360, then please do write to me. I'll just share my contact info. One moment. I think I have it here. Yes. So northwindengineering.com or drew@northwindengineering.com. So if that's it, if nobody has anything to add, then yeah, I hope this was useful, and feel free to get in touch. Let me know if you have other best practices or other recommendations. I'd be really happy to hear from you. So thank you everybody, and thank you Terja and AutoCAD for the opportunity to give this webinar.